Hello and welcome to Math200 Statistics online here at Cañada College. My name is Lapuz. In this video, we will take a look at a problem from the homework set, homework 9.6, about proportions. This is problem number 1. It says that a recidivism rate for convicted offenders is 12%. The warden suspects that this percentage is higher if the offender is also a drug addict. So out of 361 convicted sex offenders who are also drug addicts, 58 of them became repeat offenders. What can be concluded at the alpha is equal to 0.01 significance level. All right. So the first thing that we would note is, the first thing that we should figure out is what kind of distribution should we be using, what kind of test this is. So clearly this is going to not be a test for the mean, and the only other test that we've studied so far is about the proportion. So this is going to be a test for the proportion, and whenever we do a proportion, we do a z-test. So we'll call it a z-test for proportion. And in your calculator, to get yourself ready, this is going to be a 1 proportion z-test. Okay, so we do have a proportion given here, and we got 58 out of 361. All right, so our null and alternative hypothesis, how is that going to look like? We are looking at the rate of sex offenders right now, and the warden suspects that this is higher than the regular rate. So for that, we will identify the claim to be that the proportion is higher than 12%. And so let's write that in terms of the null and alternative hypotheses. And so the null hypothesis we'll call H0, and alternative hypothesis we'll call HA. And this claim here has no condition of equality. It doesn't say anything about an equal sign, so that will fall onto the alternative hypothesis, and mathematically you would say P is greater than 0.12. Now your null hypothesis will contain a condition of equality, so it depends on what your choices are. This could be a greater than sign, or less than or equal to sign, as what is the opposite of the greater than sign, or it could just be a regular equal sign, which will also convey the same message. And since this is the claim, then we can assign the null hypothesis to be a regular equality. All right. Now it's time for us to do some calculator work, or in our case, some computer work using Google Sheets. We are going to want to identify the test statistic, and since this is a z-test, our test statistic will be a z is equal to whatever that is. All right. So in this particular formula, our z-test statistic, let's call it TS, is going to be a z formula, and this will be the p hat value that we get, and we'll talk about how to get p hat minus p divided by the square root of pq divided by n. All right. So p hat is obtained by the number of successes divided by the total number. So that's x over n. And so that's 58 divided by 361 in our case. And our p is equal to 0.12. That is the value that comes as our null hypothesis. All right, so once we have those, we punch it into the calculator or to our Google Sheets. Now, just like before, I will have a template for this. And the template here, you'll input the number of successes, the total number n, your assumed proportion, population proportion. Let's extend this real quick. So your assumed population proportion from the null hypothesis. And here it's going to ask you which tail it is. Now, along the process, we will need to figure out what p hat is, and that's the value of x divided by n. So right now it's giving us a 0, but x divided by n are going to be these values over here. It's giving us an error because we're dividing by 0 at the moment, but we'll change that. Our t distribution will be the difference between the B9 and B6. So it's going to be the difference between the p hat minus the p-value, which was given as part of the null hypothesis. And then we're going to divide by the square root of pq. Now, p is given here, but q is actually going to be 1 minus p. So we didn't explicitly compute q, but we can do that also off to the side if we need to. And then divided by n, so this is all under square root, and then the result is going to be your test statistic. Now, depending on what your tail is, you would put your test statistic into the norm.dist, and so as a last step here, to find our p-value, if we have a left tail test, so that's a -1 for this value. If we have a left tail test, then we're just going to get the norm cumulative distribution on the left side. If it's a two-tail test, then we're going to just look at the negative value of it and look at the area to the left, but we're going to double it because it's going to land on two tails. So this is going to be 2 times that. And then if it's a right tail test, then it's going to be the complement of the area on the left. So we find the area on the left and we take the complement of that. So that's the 1 minus. And then we're going to get the area on the right tail. So that's a little bit of the code for this little workbook. Now let's put in the values that we are given. It looks like, if you remember, the number of successes we had was 58. And the total number that we pulled was 361. Our null hypothesis was 12%, so let's put 0.12 for the 12%. And then we are looking at a right tail test, so we will type in the number 1, and then here are the values. So just immediately looking at the sample proportion, we're looking at 16%. That's bigger than 12%. Now this whole test is actually checking, is it really significantly bigger than 12%? Or is it just slightly bigger than 12% and it's really not out of the ordinary? So that's our decision-making process. All right, so we did get our test statistic here. The test statistic is going to be 2.3776, and rounded off to 3 decimal places, we'll probably say 2.378. So we'll go with 2.378. I want this in red. It's 2.378. 0.378. So whenever we get values that are less than, that are bigger than 2 for our test statistic, then we're looking at these things to be kind of far away from the middle. And your p-value will show that. And so technically, what's happening here is that this value around 0, and this is 2.378. That's your right tail shading in. And so the area here is going to be your p-value. And since it's more than 2 standard deviations away, we would expect that to be fairly small. And in fact, it's going to be 0.0087. So our p-value is 0.0087. Okay, which is small. Now clearly our p-value is less than alpha, so PV less than alpha. And so because of that, we will reject the null hypothesis. We're going to reject the null hypothesis. Now, since we rejected the null hypothesis, this is what we're looking at. We rejected the null hypothesis, so we should be able to support the claim that the proportion is in fact going to be bigger than 12%. So the data suggests that the proportion is significantly higher than 12% at a 0.01 significance level. So there's statistically significant evidence to conclude that the population proportion of convicted sex offenders, drug addicts who become repeat offenders is higher than 12%. So I think that is it. And if we just take a scan at the other options, the data suggests the population proportion is not significantly higher. Well, I don't think we're doing that. And then the last one is also a not significantly higher. So I think our solution here for this one is that we're going to be able to say that the claim, we'll be able to support the claim that it's bigger than 12%. And here are a couple more questions. Interpret the p-value in the context. So the p-value is 0.0087, so that's 0.8%. That's less than 1%. The p-value is not a type 2 error, so let's go ahead and take that out of the mix. 0.087, that's a p-value, chance of more than 12%. This one did not really mention the n value, and usually we want to include the n values here. So it looks like the last two are the two options. First one, if the sample proportion of convicted sex offenders become repeat offenders is 16%. Well, I think it's not 16% that we want. We want to compare it to the 12%. And so it says here there would be a 0.87% chance. So I don't think this is what we want. Let's take a look at the last one. If the population proportion of convicted sex offender drug addicts who become repeat offenders is 12%, and if we choose another 361 convicted sex offender drug addicts are surveyed, then there would only be an 8.7% chance that more than 16 of them will be repeat offenders. So this is our correct choice for this one. Now the last one, it says interpret the significance level. Again, unfortunately, our significance level is actually the type 1 error, but that's not one of the options. So let's read through a couple more of these options. There is a 1% chance that the proportion, so again, these things don't mention anything about the sample size, which is really part of the statement. 1% chance that lizard people are running the world. Let's go ahead and cross that one out. All right, this next one, if a population proportion of convicted sex offenders become repeat offenders is 12%, and another 361 sex offender drug addicts are observed, then there would be a 1% chance that we would falsely conclude that the proportion of all sex offender drug addicts become repeat offenders is higher than 12. So I think that's it. This is essentially the type 1 error statement that does match up with the significance level. So this is the correct choice. All right, so I hope that is working, and I hope that makes sense. And that's it. Good luck.